Today we're going to look at the different types of reactions you will see in this course. There's kind of 5 different major styles or types of a reaction, and I've got them on the screen here: synthesis, decomposition, single replacement, double replacement, and combustion reactions. And knowing these kind of 5 different types of reactions will help you understand kind of what's happening with the chemicals when they're reacting, and like why certain chemicals are switching spots with each other, that kind of thing. So there's some patterns here. Now, not all reactions are one of these 5 types, but for this course, that's what we're going to focus in on these 5 major types of reactions. So the first one is called synthesis, and when you're synthesizing something, you're basically combining them directly. So you're taking 2 or more substances to produce one thing out of them. So if you had a general form, for example, like if we just made up a kind of a generic reaction, it would be A and B comes together to make AB. So a kind of a real world example is where you would have nitrogen and hydrogen forming ammonia. So we have nitrogen molecules, hydrogen molecules, and then they come together to form one compound called ammonia. So we're taking 2 or more things to put them together to make a single thing. And I'll show some of these demos in class, but if we wanted to see an example of that as an animation, I'll show you what this kind of looks like. So here is an example of a synthesis reaction. Just let this load up. So here is oxygen gas and hydrogen gas. These are 2 simpler substances. I'm going to let them react with each other, and eventually the particles will collide with each other, and we can form a product from them. Oh, there we go. We've just formed 2 waters. Now notice, in order for the reaction to happen, the particles actually have to collide, and they have to collide the right way. But there's our products making our reactants. So we took 2 simpler reactants and made a more complex product. We're kind of combining things together. If you think what a synthesizer is in music, it literally takes a bunch of different sounds and puts them together to make a song. So in real life, here's an example of the synthesis. This kind of example is getting old, but Brad and Angelina used to be together, and they were actually called Brangelina. That's what all the TMZ shows and stuff are calling them. So this is 2 people, individuals, got together to make a couple, and we gave that couple a special name. Now, the opposite of synthesizing something is decomposing something. You're breaking it down. So we're taking a single compound, and we're breaking it down into smaller parts, into 2 or more different substances. So an example of this would be potassium chlorate to make potassium chloride and oxygen gas. So notice I'm taking this more complex molecule or compound and breaking it down into smaller compounds. If we wanted to see what this would look like in terms of a reaction, this is decomp. Here we go. So in this test tube, we've got copper hydrogen carbonate, and if I heat that, we can actually cause it to decompose. So we're taking the carbon hydrogen carbonate and we're breaking off waters and carbon dioxides by heating it. And if we let this go, it should show us what the actual reaction is after this is decomposing. So what we're left with is copper oxide. We released carbon dioxide and water as well. So we took this compound and broke it up into 3 smaller compounds, and that's a decomposition reaction. Okay, so now we'll go back to our example. So if we use the Brad Pitt analogy again, before Angelina Jolie was around, he was with Bennifer. He was part of this couple named Bennifer with Jennifer Aniston, and then they split up before he went with Angelina Jolie. So Brad and Jennifer got separated. That relationship decomposed, if you will. Sounds kind of sad. Now, single replacement is where you have a single, in like an individual, switching place with somebody out of a couple. So if you look at this the example that I have here, sodium is switching spots with magnesium. Sodium takes magnesium's place and magnesium goes to sodium's place. You'll notice that we always switch metals with metals or nonmetals with nonmetals. So an example of this in a real reaction looks something like this. So we have copper metal and silver nitrate. So our metals are going to switch spots. So copper goes to where silver is, and silver is going to go out. So I'll let this react. So you'll see the silver ions come in, and once they hit the copper will switch spots and go into the solution, and the silver comes out of the solution. So copper goes with nitrate and silver goes back out by itself. You'll also notice that this solution is actually getting more and more blue as this reaction progresses, and that's because copper ions, when copper is dissolved, it forms blue solutions. So that's why you're seeing it get more and more blue as this reaction happens. And there's our last pair, and that reaction would now be completed. Okay, so looking at a reaction, you can see silver and copper are switching places. The way we look at this is you have a metal and a non-metal group. So this is almost like a couple dancing, and this guy, girl, is switching partners. So they're cutting in and taking silver's spot. So silver goes off on its own and copper is taking its spot. Now, if we were going to use the Brad Pitt analogy again, you could actually think of this whole synthesis and decomp thing as one big single replacement reaction, because you had Bennifer and Angelina was on her own, and it switched. Angelina and Jennifer switched spots, so Angelina went with Brad Pitt and Jennifer was off on her own. Now, double replacement is where you have two couples. Imagine you have two couples dancing and they swap partners. Now, we're always going to make sure that we end up with a metal and a non-metal because they're opposite charges and opposites attract. But this is kind of a general form. So notice that aluminum and calcium basically switch spots. Aluminum ends up with a hydroxide and calcium ends up with this sulfate. So if we were to show you an example of this one, it would look something like this. So in this one I have a lead and nitrate, and this one I have potassium and iodide. And if I combine them together, we're going to see those two couples switch partners. Okay, so all of these ions are now mixed all together, and eventually the leads and the iodines are going to bump into each other, and they're going to form a new compound called lead iodide, or lead 2 iodide, I guess would be the correct term for it. Lead iodide actually is a solid, so it sinks down to the bottom, and then the rest of it stays together. So you're going to get lead iodide and potassium nitrate. And again, notice that we always end up with metals and nonmetals together. So we're switching it up so we end up with a metal with a nonmetal, because we'd rather have opposite charges together because that forms a better attraction. So lead switches with potassium, so lead goes with iodine, potassium goes with this nitrate, and that's what we get on the product side. Okay, so now here's a kind of a similar analogy. So if we look at what we've got here, we've got pink panther and black eye makes a black panther and pink eye. So what we're doing is we're switching the colors, right? Just like before we switched the metals, here we switch the colors. Black goes with panther and pink goes with eye. So there's an example of a single or double replacement. We're switching both partners. Now, the last one is called combustion. Now, a lot of people think combustion is an explosion, but all it is that the reaction of a hydrocarbon with oxygen. And we always, nothing ever changes here. It's always making carbon dioxide and water. So it has to look something like this example here. Some hydrocarbon, C's and H's, reacting with oxygen to make CO2 and H2O. It has to look like that. This is basically any sort of burning of fossil fuels that we do. So burning natural gas for your furnace, burning gasoline in your car, burning propane for your barbecue. These are all examples of hydrogen or hydrocarbons, and we're burning them. And if you think about if your engine's running perfectly, the only thing coming out of the engine of the car is carbon dioxide and water vapor. So that's basically what should be coming out of the tailpipe. Now, this is not a perfect process. Your engine isn't perfect. There are other pollutants in there, and gasoline is not 100% pure. So there are other things that are produced. But if you have a perfect reaction between those two chemicals, that's what you would get. Now, if we're going to balance combustion reactions, they are a little bit trickier. So follow that macho process that we looked at. In other words, we're going to do carbons, hydrogens, oxygens. There's no metals in this, so we're just jump right to the CHO part. So when I balance these, I'm going to look at the carbons first. There's a 3 there, so I put a 3 in front of my carbons. Now I'm going to do the hydrogens next. There's 8. So to get 8, I put a 4 in front of the water. So now I'm going to count up my oxygens. 3 times 2 is 6, and 4 more. 6 plus 4 is 10. So to get 10 over here, I got to put a 5 in front. Let's try the next one. C2H6. So I'm going to put a 2 in front of my carbon. Now my hydrogen, there's a 6, so I got to put a 3 there. So let's count up our oxygens. 2 times 2, that's 4, plus 3 more is 7. Something times 7, or something times 2 is 7. Well, that doesn't work because it ends up being 3.5. So what we're going to do is we could put 3.5 here, but what we need to do is we need to double everything because we can't have a decimal. So what I'm going to do is I'm going to double everything. And then that will make it whole numbers. If you double a half, you get a whole. So now let's check. We have 4 carbons, 4 carbons. We have 2 times 6 is 12 oxygens, 12 hydrogens. 6 times 2 is 12 hydrogens. And let's check our oxygens now. 4 times 2 is 8, so that became an 8. 6 more, that's 14. Well, 7 times 2 is 14, so we are now balanced. Give this one a try and check your answer with mine. So I'm going to balance my carbons first, so I put a 6. Then my hydrogens, I put a 7. I can already see that I'm going to end up with an odd number of oxygens. So I have 12 here and 7 more is 19. That doesn't work. So I'm going to double these. This one's now doubled, so this becomes a 12. This becomes a 14. I've got to double everything. Now let's check our oxygens. This becomes 24. 14 plus 14 more is 38. That means this would have to be 19. 19 times 2 is 38. And that's about as hard as they can get. It'll just look like that.